Okay. Okay, I'm back. Everything back. Stream health good. You can hear me again. Okay. Okay. So yeah, I think things worked out. I figured something out. And the screen is working again. Okay. So question 44. Oh, what did I do with my? There it is. Okay. So question 44 goes like this. There's an object coming down. It starts up here, and then I copied out the diagram for it. Comes down, and then it goes back up. Then it comes down, it speeds up. When it goes back up, it slows down. What does this look like to you? How about, we need a story. There's lots of different stories you could tell. How about this one? I throw a tennis ball down, and the tennis ball falls and speeds up as it's going to the ground, and then it hits the ground, and it bounces. And as it rises, it slows down to a stop. This is just a small chunk of the story, of course, and however, because the story goes, immediately after it would start going back down again. But whatever. This particular motion diagram only cares about these two things, and that's the story I'm going to tell with it, and I hope that's okay with you. So, next question. Let's see. Oof, all that drama. That was question 44. Now it's question 53. Question 53 goes like this. Motor neurons in mammals transmit signals from the brain to skeletal muscles at approximately 25 meters per second. Estimate how much time in milliseconds it will take for a signal to get from my brain to my hand. So there's my hand. I guess I better draw my brain. Brains are pink, right? So there's my brain in here. And then there's a neuron that comes and it goes down my shoulder and up my arm into my hand. So the question is, how long is that? Do I have a tape measure around here? I do. Let's see. Tape measure. I thought I had one. Got a ruler, but that won't work. Let's see. Maybe it's in the straw? Oh, this isn't good. Okay, I don't know how long I don't know where my tape measure is. So I guess I'm gonna have to guess. Let's see, I'm about 2 meters tall, give or take, and the hand span is about a meter. So let's go with this distance down my arm is about go 1.2 meters. How about that? So the displacement of the signal is going to go, it needs to travel that far. And the average velocity is 25 meters per second. And so delta x is equal to v delta t, so that's 1.2 is equal to 25 times delta t. So delta t is equal to 1.2 over 25. All right, and it wants it in milliseconds. So this is in seconds, but the answer here is going to be 48 milliseconds. That's my guess. I don't know. All right, question 55. 55 goes like this. Really? I want to do 55? I thought I was doing a different one. All right, let's see. Question 55 goes, oh wait, I should open the thing and see if anybody has any questions. Any questions? Anusha, you got any questions? Wait, 0 people are watching. Oh, that's no good. Well, I don't know. The stream changed. I think this should stack on the previous stream, but I don't know the answer to that. Anyway, I guess for posterity then. So question 55 goes like this. Your brain communicates with your body using nerve impulses, electrical signals propagated along axons. Axons come in two varieties: insulated axons with a sheath made of myelin, and uninsulated axons with no such sheath. Myelinated sheathed axons conduct nerve impulses much faster than unmyelinated axons. The impulse speed depends on the diameter of the axons and the sheath, but a typical myelinated axon transmits nerve impulses at 25 meters per second, and unmyelinated it's 2 meters per second. Figure P155 shows 3 equal length nerve fibers that look like this. Here's one, here's the other. It's got myelin on it. Draw myelin nice. Okay, so the first one looks like that, the second one looks like that, and the third one looks like that. They're the same length, but this one has myelin on it part ways, and this one has myelin on it all the way. 8 axons in a row. 1, 2, 3, 4, 5, 6, 7, 8. Fine. Nerve impulses enter at the left side simultaneously and travel to the right. So you bring your poker stick over here and you poke the axon over here, and then the impulse travels to the right. Okay. Draw motion diagrams for the nerve impulses traveling along fibers A, B, and C. So along A, it's going to look like this. Constant velocity, traveling pretty slow. For C, it's going to look like this. It's going to go super fast all the way there. And also this isn't to scale, because you know that these ones are 10 times faster. But whatever. So what about B? B, it's going to travel fast the first bit, but then go slow the second bit. Which nerve impulses arrive first at the right side? This one's a winner. Goes faster. Which will be the last? This one's going to be the last. How do you know? Because it takes much more time for more dots, takes more time. This one has fewer dots, it takes less time. This one has an intermediate number of dots. Each dot is taken with, I don't know, some delta t time interval between them. So yeah, this one takes less time, this one takes more time. Hooray! I'm kind of bummed that nobody's watching. I wonder why. I hope this works. All right, next question is, let's see, that was 55. Next question is question 62. Oh, this pen looks nicer. John walks 1 kilometer north, then turns right and walks 1 kilometer east. His speed is 1.5 meters per second during the entire stroll. What's the magnitude of his displacement from beginning to end? If Jane starts at the same time in the same place as John, but walks in a straight line, what speed should we walk to arrive at the end point where John does? Okay. So, John starts here. Hello, I'm John. Maybe it's John Hopkinson, the professor. So he goes 1 kilometer north, so that's 1,000 meters. And then 1,000 meters east. How far is it from here to here? Oh hey, that's a right triangle. Square root 1,000 squared plus 1,000 squared. Take out calculon, the calculator. 1,000 times square root of 2. So this red line's this long. How much time does it take John to make this trip? Well, John is walking at 1.5 meters per second. So this leg of the journey takes delta t, delta x 1,000. Delta t is unknown, and v is 1.5. So delta x is equal to v delta t, 1,000 divided by 1.5 is equal to delta t. So that's 666 seconds. Takes them 666 seconds to do this part, and this is the same distance. So delta t here will also be 666 total time. That's equal to 13333 seconds. So John's friend, what's her name? Jane. Jane's going to walk this way. And she's going to start at the same time, and she wants to reach here at the same time. But she doesn't want to travel, well, I don't know, she's just more straightforward. Jane, so what average velocity should she have? It's going to be delta x is equal to v delta t. So it needs to be 1414 meters divided by 133. How many threes? Yeah. I got over-enthusiastic writing threes. 1.06 meters per second. It's not hard, is it? Good. Live stream offline. What? Why? Can you hear me now? What's this? You see that? Jeez. It says I'm streaming now. I don't know. No one's watching. Can you hear me now? Alright. Still nobody's watching, but 10 minutes in, that's not too bad. Okay. So let's go to chapter 2, I guess. Chapter 2, question 6. So this is on page 65. Question 2 says, question 6 goes, certain animals are capable of running at great speeds, other animals are capable of tremendous accelerations. Speculate on which animal would be more beneficial to a predator, large maximum speed or large acceleration. What's better? Okay. So, I think it depends on what kind of animal you are. Well, let's say there was a gazelle. And the gazelle standing in the grass. The grass is really high here, and you can get really close, really quietly. Then having faster acceleration than your prey would be useful because you can hop on them before they notice you. And what's more, if you've got really good acceleration, if your prey sees you and goes that way, you can follow right after them. So acceleration is pretty useful in that way. What if you're a... Well, let me propose an alternative method for hunting. This is the one some birds use, like eagles, peregrine falcons, stuff like that. You know, hey, I am a mouse. Mice are notoriously good accelerators because there's not much to them. So they're really prancy. But what you can do here is, it might take you a while to accelerate, but if, when you're flying, let's see, hold on. Yeah, there you go. If you can go really, really fast, then you might be able to sneak up, well, not even sneak up, before this guy has even realized that you're around, before he's even heard you or processed it, if you're on top of him, hey, that's pretty good too. So which one's better? I don't know. This one's pretty good, but so's this one. I think it depends on what kind of prey you're eating. Certainly, you always run the risk of the prey going that way, right? And so if you don't have very good acceleration, you might be coming at the prey, and the prey doesn't even have to move very far to get out of your way. But if you're fast enough, that probably doesn't matter. I don't think land animals can really travel fast enough to do that, but some birds probably can. Like, I know the peregrine falcon goes super, 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 super fast and gets its prey like this. So I don't know what the answer is. The answer is, I think it's up to you. That said, could work. You got it. Yeah, I think the answer they're probably looking for is acceleration though, because lots of animals hunt like this, ambush hunters, and also you want to be able to follow your prey if it changes direction. If you're a prey animal, running really fast for a long time is pretty helpful, but it won't really get you out of the fact that there's tigers everywhere. So instead, if you're like, you ever look at like a rabbit's spine? It's shaped like that. And the reason rabbits are shaped like that is because they're literally always coiled up, ready to ready to bounce. Um, Rabbits, they can't run super fast. I don't know if a human can outrun a rabbit, but their mode of locomotion, if you hadn't noticed, is hopping, hop, hop. And that's because hopping is, it lets you, if you're built for it, it lets you change direction and accelerate really quickly. So if there's, say, oh no, are you going to draw a lynx? Yes. Look, it's a lynx. If you're a lynx falling behind it, the lynx can't keep up with all your rampant acceleration. So even though you're in the general area of the lynx, you can still not get caught. Hop, 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 hop. The lynx falls down. Oh no, I twisted my lynx ankle. And then you hop away. All right. So I think the answer they were looking for is acceleration. But if you can go fast enough, you can eat anything you want. That's right. Question 12. I wonder if anybody should be getting mad at me for half-assing the biology part of this. Okay. Oh, 12 is super boring. It's an X versus T question. I'm going to check on the health of the stream right now. It says it's streaming. Okay, well, cool. And 2 people are watching. That's cool. So, yeah. All right, this question goes like this. Position versus time graph looks like this. And there's some places that they want to talk about. They want to talk about here, A, here, B, here, C, here, G, here, E, here, F. It shows a position versus time graph at which letter time or point is the object moving fastest. All right, so how can you tell if something's moving fast in a position versus time diagram? You look at the slope. Fast moving doesn't mean moving uphill. Fast moving just means big slope. So I think A, C, and D, it's moving fastest. Question B. Moving to the left. Oh, they didn't even define the coordinate system. So let's say the negative direction is left. So when is it moving to the left? C, D, and E, it's all going downhill. C, D, and E. Speeding up. So to tell if it's speeding up, you compare the adjacent ones. So here it goes from big slope to no slope, so it slowed down. And from B to C, it speeds up. I think C, you know what, I'm going to write it like B to C, it's speeding up. And C to D, it's speeding up. And D to E, it's slowing down. D, when is it slowing down? It's slowing down from A to B, because it starts out with a big velocity and then it goes small. And then from D to E to F, it goes from a big slope to zero slope. So D to E to F. When's it turning around? So what do we mean by turning around? Turning around means that the velocity is changing from positive to negative. Okay? So where in this do we see the slope going from a positive slope to a negative slope? That's right, it's at B. All right, so that's 6 and 12 done. Now we go to page 67 and do question 3. Write a short description of the motion of a real object for which 2.3 would be a realistic position versus time graph. 2.3 looks like this. Oh, what just happened? I brushed against something. 2, 4, 600. So I'm going to copy off the graph so that I can point to it and wave my hands. So the graph looks like this. It's a straight line here, and then it's flat, and then it goes down like that. All right, so it wants a real-life situation that looks like this. What real-life situations look like this? That's the question. So, what's the answer? Well, one issue here is how long it takes to go anywhere. 300 seconds, that's about 5 minutes. So 300 meters in 5 minutes. That's kind of walking speed, isn't it? So if you're traveling that fast, it's, I don't know, you probably go a kilometer in about 15, 16 minutes, which is pretty slow. And then it stopped for 100 seconds. And then you go 300 meters in, so the last part you're going 300 meters in 200 seconds, which is about 3 minutes. So in this case, you're traveling, let's see, and it takes about 10 minutes to go 1 kilometer. So this is kind of jogging speed. So here's a story. A person starts out at home. They gotta get in. They gotta go to work. So they start walking towards work. They aren't walking very quickly. And then after 5 minutes of walking, they're 300 meters along. They're over here, and they're like, "Oh no, I forgot my wallet." And so they well, hold on. They stop on the local park bench, and they take everything out of their purse. Here's their purse, and they're like, "No, these are my keys. It's not my wallet." And so then they're like, "Oh no, I forgot my wallet." And then so after about almost 2 minutes of looking through their purse and not finding their wallet, they jog back home to get their wallet, and then they can go to work. late. Okay, next question. So that was 3. I've already done 7. We did 7 at the very start, accidentally. So now it's question 11. Okay. Oh, it's in. Great. Okay. Alan leaves Los Angeles at 8 a.m. to drive to San Francisco, which is 400 miles away. He travels a steady 50 miles per hour. Beth leaves at Los Angeles at 9 a.m. and travels a steady 60 miles per hour. How long? Who gets to San Francisco first? And how long does the first to arrive have to wait for the second? This is a fun question. Okay, so I am going to draw this distance from 0 to 400. I'm going to start by sketching it. So there's 200 miles, and then there's 100 miles, there's 50, 150, 300, 250. So there's a variety of different ways we could use to tackle this problem. It's actually pretty delightful. I'm going to start using the motion diagram method. So at t is equal to 8 a.m., and then I'm going to draw, so these black dots represent Alan's position. And he goes 50 miles an hour. So at 9 a.m. he's here, 10 a.m. he's here, 11 a.m. he's here, 12, 1 p.m., 2 p.m., 3 p.m., 4 p.m. Okay. So then Beth leaves LA at 9 a.m. So it's 9 when she leaves. But she goes 60 miles per hour. So her displacement is going to be slightly bigger. So there, that's going to be 10. And then 2, 3, 4, 5. There, it's going to be 11. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. Oh, I know what I did wrong. Oh! Should be. Let me do this diagram on. There should be 4 notches in between it. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. All right. So at 12, she's 3 up. And at 13 hours, she's there. And at 14 hours, she's there. And at 15 hours, she's there. And then at 16 hours, she's over here. Okay, so this means that Beth reaches this point at 400 faster. So Beth wins. How long does she have to wait? Well, to figure that out, I need to know exactly what time she reaches there. So I can actually figure that out off this diagram. She goes 1, 2, 3, 4. There's 400 for 40 miles divided by 60 miles per hour. That's That's 0.6 hours. So she reaches this point at 15.6 hours, and then he reaches that point at 16 hours. So she waits 0.4 hours. 0.4 times 60, which is about 24 minutes. That's not a very good way to do this question. So there are other ways that may or may not be better, depending. The easiest way is algebraically, so we'll get to that last. An alternative way is to draw a graph that looks like this. So here's 400, 200 miles, 100, 300, and in hours. So this is hour 9, no, 8 hours. We started 8 hours. So we start at 8 hours, time in hours, and then this is position in miles. Feet. Uh, 9 hours, 10, 11, 12, 13, 14, 15, 16. So what you can do is you can draw, what's the guy's name? His name is Alan. Alan's position versus time is he goes 100 miles in 2 hours. And you draw that graph and it looks like there. And then you draw Beth's graph. Beth is going to start at this time, but she has a bigger slope. And so she goes, in 1 hour, she goes 60, which is like that. So she's going to go like, and then you graphically estimate where and when they meet. So on this page, you can't see it because, frankly, freehand is no good for drawing graphs if you want to interpret them. But if you had proper graph paper, you could do it. The third method is pretty fun, and that's to use these equations. We know that the position versus time graph is a straight line. So position is initial position plus v times t. Okay. This is actually written in terms of the x-intercept. So that in terms of when it reaches the vertical axis. So for Alan, position versus time is going to be 0 plus your velocity, which is 50, times the time, which is the current hour minus 8. What's with the minus 8? Well, the thing about this axis is it's a truncated axis. Sometimes you see these on the news when they want to mess with you. But essentially, if I were to draw this starting from t is equal to 0, I'd have to draw quite a bit, right? Because this is like 7, 6, etc. And they don't show up until t is equal to 8. So I just left that part of the graph out. Doing it this way is a method. Sorry, like I said, okay, so you're probably familiar with y is equal to mx plus b, right? This is called slope-intercept. Form. And it's called slope-intercept form because there's the slope and there's the intercept. But in that case, this is the intercept on the vertical axis. You can also write a straight line using a bunch of different ways. This one's called point-intercept form. X minus x0 plus y0, where x0 and y0 are just any point that the graph goes through. Or I guess in this case, it would be t0, x0. Okay? So the long story short is, when I read this out, I'm using the point-intercept form of a line. So I know that it's at position x equals 0 at time t is equal to 8. And I just plug in this equation. And that means Beth's position versus time is they're at position 0, that's LA, 60 times t minus 9. She leaves at 9 o'clock in the morning. And then I can use these equations to figure out when they arrive. So they're going to arrive at when x is equal to 400. I think that's arrival, right? So that's going to be 50 times t minus 8. And so you can calculate Alan's arrival time as 16. And then for Beth, x is equal to 400. It's equal to 60 t minus 9. So 400 divided by 60 is 6.66. It's equal to t minus 9. So t is equal to 15.6. So they arrive first, because it takes them, I mean, this is the time when she arrives, in decimal time. So how long does she have to wait? 0.4 hours. Okay. And, is that the last question? Oh, still one more. Question 18. How's the stream health in this? Is it still streaming? Yes, it's still streaming. And 2 people are watching. Hello. Question 18 goes like this. So, is this the right question? Yeah, it is. A somewhat idealized graph of the speed of blood in ascending aorta during the beat of a heart appears in 2.18. So this is what the graph looks like. Not. Okay. So this is the velocity. What do they talk? The speed. Well, or whatever. So what they're doing here is they're like, hey, what does the heart look like? It's got 2 chambers, right? Wait, how many holes are there in a heart? There are 4? Let me look at the diagram of a heart. Human heart. 4 chambers, right? Yeah, look at all those chambers. Sweet. Okay. So, oh yeah, okay. All right. So you got outgoing, this one, and then you got another one that goes out this way. So they're talking about this. Essentially what they do is they say, hey, how fast is blood passing through there? And the answer is your heart beats, so it gets really thin, as it pushes blood out. Okay, and it looks like this. That's the velocity versus time as blood leaves the heart and goes to your aorta. Great. Anyway, Approximately how far in centimeters does the blood move during one beat? Alright, so what are we talking about here? Displacement. Talking about displacement. So if blood's moving through here with this time signature, we want to know the total displacement over one beat. So that's the area in this. It's a triangle. How wide is the base of the triangle? The base is 0.2. How tall is it? 0.7? So the area is equal to 1/2, 0.2 times 0.7. So that's 0.07 meters. Good. So the blood goes they want it in 7 centimeters. 7 centimeters. That's how far the blood goes. In other words, blood's coming out of your heart. Every time the heart beats, what we're trying to say is to your brain. Every time the heart beats, the blood is advancing down this column about 7 centimeters. That's fun. Assume similar data for the motion of blood in your aorta. Estimate how many beats of the heart it would take for the blood to get from your heart to your brain. Well, what's the distance between the heart and the brain? Sounds like a love song. What is the distance between the heart and the brain? You can think about it, but the answer will be the same. I just don't love you. I gotta go my way. So if you can send all my stuff to my mom's tomorrow or another day. Okay, so I don't know, how far is it from my heart to her brain? Let's see. I don't know okay, let's try drawing this. Here's your heart. Hearts are shaped like upside down hearts. Here's your brain. That's let's see, maybe there. It's about a foot, maybe 20 centimeters. So it takes about 3 seconds. If the blood is traveling 7 centimeters per beat, and it has to go 20 centimeters, it's going to take about 7 beats. No, wait, 3 beats. There's only 3 beats between the heart and the brain. When your heart gets broken, you don't feel the pain for 3 beats. Alright, that's it. That's it for the online office hours this week. I hope you had fun. Hopefully next week there won't be as many technical issues. I can't believe we wasted so much time on those this week. But now you see the format. Essentially, it's just me doing problems and you complaining that you can't hear the sound over the mic. Okay, see you, everybody. Boop, boop. No, wait, hold on. Boop, boop.